Hi, in this video we are going to talk about the applications of shortest path algorithms. So let's get started. We have seen how to use shortest path algorithms to detect arbitrage situations in stock market, but apart from this application there are several applications of these kinds of algorithms. So if the graph is a DAG, a directed acyclic graph, so there is no directed cycles in it, it is easier to find the shortest path. That's what's called the topological shortest path. So we sort the vertices into topological order. We iterate through the topological order, relaxing all edges from the actual vertex. And this algorithm is used, for example, for knapsack problem. We can reduce the knapsack problem to a directed acyclic graph. And after constructing that graph, we just have to run this algorithm. And this graph is always directed and there's no cycles in it. So we can use this topological shortest path, which is very fast. So topological sort algorithm computes shortest path tree in any edge weighted, can be negative. That's why it's good. DAG in time O E plus V. So it is a linear time complexity where E denotes the number of edges and the V is the number of vertices. It is much faster than Bellman-Ford or Dijkstra's algorithm. So it has several applications, as I said earlier, for example, how to solve knapsack problem. There's the Evidence-Shamir method. When we want to shrink an image, for example, in the browser or on a smartphone without distortion, that's the problem. And how can we solve it? We want to make sure the image will not deform, and we have to eliminate the least significant bit strings. So how can we find the least significant bit strings? We set up a so-called energy function and remove the connected string of pixels containing the least energy. Photoshop and GIMP use it on daily basis. So we build a huge graph. Vertices are the pixels and the edges are pointing from every vertex to its downward three neighbors. Like this, I'm going to show you, like this. Of course, when the pixel is the leftmost or the rightmost, there will be no left child or right child, so we are going to make these connections accordingly. So we build a huge graph like that, and the energy function determines what the edge weights will be. And this graph is acyclic, so we can use the topological order shortest path to find the string of pixel to be removed. So we are going to construct this huge graph. We just have to run our topological order shortest path. And why is it good? Because as we have discussed earlier, it's very fast. Dijkstra's algorithm is not so fast, let alone Bellman-Ford. Bellman-Ford is a quadratic complexity, but topological order shortest path is very, very fast. So that this is how we came to the conclusion that what pixel of strings to be removed. So this is the graph, for example, for Evidence-Shamir method. And there's another application, the so-called longest path problem. We just have to negate the edge weights and run the shortest path algorithm. So we have to use Bellman-Ford because negative edges can occur due to the negation process. And there's a very, very important application, the parallel job scheduling problem. And lots of, for example, car engineering factories and software engineering softwares are relies heavily on these longest path problem. So given a set of jobs with durations and precedence constraints, schedule the jobs by finding a start time to each so as to achieve the minimum completion time while respecting to the constraints. So for example, let's consider a factory where we have to engineer, for example, a whole car, and it took some time to make the doors of the car. It took some time to, for example, handle the tires and so on. And of course, there's a procedure that some processes have to be after others. So this is a typical parallel job scheduling problem, and we can solve it with the help of longest path algorithms. And of course, the critical path method, the so-called CPM, we create an edge-weighted directed acyclic graph, add edges with zero weight for each precedence constraint. We have to find the longest path in order to solve the problem, and there are no cycles in such a graph, and this is why it is a directed acyclic graph. So we can use the topological ordering shortest path problem. So these are the applications of the shortest path problems and how to reduce lots of problem to the shortest path one. So thanks for watching.